And here's on your own 6.3. It's on page 171. It says citric acid, which is C6H8O7, is a component of fruit drinks, jams, and jellies, and it's produced using the following reaction. I wrote it down on the board. Sorry, I ran out of a little bit of room for my products over here. If a fruit drink manufacturer decides she needs, okay, this is what we know. We know we have 1.4 times 10 to the 5th moles of citric acid, C6H8O7. If a fruit drink manufacturer needs that much moles of citric acid, what is the minimum amount of reactants she will need? So knowing how much of this we want to end up with, we can figure out how many moles of oxygen, water, and this other carbon compound that we need in order to come up with that much product. So we start with, let's write down, so we have to find how many moles of C12H22O11. We have to find how many moles of H2O, and we have to find how many moles of O2. Okay, and we're going to figure all that out from knowing how much product we need at the end, and then using the proportions that we have up here. We have 2 to 1, we have 2 to 1, we have 2 to 3. We'll figure out the proportions as we plug them into our equations. Okay, so let's start with 1.4 times 10 to the 5th moles of C6H8O7. That is a 7. Using the factor label method, we want moles of C6H8O7 on the bottom. And let's just start with our first reactant, C12. So we're going to figure out how many moles of C12H22O11 we need. Okay, so now plug in the numbers for the proportions. For every 2 moles of citric acid, we need 1 mole of C12H22O11. So 1 goes on the top. So we multiply or divide this out, and that answer would be 7.0 times 10 to the 4th moles of C12H22O11. Now, when you're plugging this into your calculator, if you are using an iPhone, you would put in 1.4, the double capital E button, 5, divided by 2. And then you would see your answer in scientific notation. Okay, so remember that double E button looks like this. Just a double E like that, and it takes the place of the times 10, and then your next number shows the power that it goes to. All right, we practiced that in class. Okay, so our first reactant we need that much of. Our next reactant is water. So let's set that one up. 1.4 times 10 to the 5th moles of C6H8O7 times that same unit on the bottom of our fraction, moles of C6H8O7. And on the top, what we're looking for is moles of water. Now, there's a little trick here. Remember, we are trying to find out how many moles of water are needed as a reactant. Because as I look at the products, water is also one of the products. But we're not concerned right now with the products because the question and the on your own problem asked us to find how much we need of the reactant. So we're looking at the water on the reactant side of the equation. Okay? So here we have a 1. So 1 goes with moles of water, and 2 goes with moles of citric acid. Again, I'm just looking at the coefficients. or the invisible coefficients, like what's out front of the water, the 1, to figure out the proportions there. Okay, so this one again is 1.4, then you'd hit that double E button, E, then you'd hit 5, 1.4 E, 5, then you'd hit divided by 2 equals, and it's the same amount, 7.0 times 10 to the 4th moles of water are needed for the reactant. Okay, and then our last reactant is oxygen. We need to know how much oxygen we need for this. So we start with 1.4 times 10 to the 5th moles of citric acid, which is C6H8O7, times moles of C6H8O7 on the bottom, moles of our last reactant, which is oxygen, on the top, moles of O2. Now we fill in the numbers. For every 2 moles of C6H8O7 produced, we need 3 moles of oxygen, okay? So we put this into our calculators, and we would get 2.1 times 10 to the 5th moles needed of oxygen. Oh my word, that was a long problem. Did I bore you to death? I hope not. I need something to spice all this math up sometimes. But I hope it's making sense to you. Remember, this is stoichiometry, and we will be spending this module doing more stoichiometry, but we'll be done with it fairly soon, and we'll move on to something else. On your own, problem 6.2. The first step in a long process that converts iron ore into pure iron involves converting iron ore into iron oxide. This step is accomplished through the following chemical reaction. Let's write it down. 4FeS2, this is on your own 6.2. So we have 4FeS2 plus 11 oxygen, which remember, oxygen is never just O, it's always O2, plus 11 O2 yields 2 Fe2O3. This is the iron oxide, one of the products, and the other product is 8SO2, sulfur dioxide. Okay, so if an iron manufacturer starts with a certain number of moles of iron ore, this is the iron ore, how many moles of oxygen will be needed to completely react with the iron ore? Okay, so we are going to find how many moles of oxygen are needed here. And then secondly, it's asking how many moles of iron oxide are produced. How many moles of Fe2O3 are produced, okay? So let's figure that out. We start with what we know. We know how much do we have to start with? 1,256.0 moles of iron ore, FeS2. And then of course we know the proportions between FeS2 and oxygen is 4 to 11. I'm just going to write just the numbers down just so we remember that we know these proportions. And then we know the proportion between iron ore and iron oxide is 4 to 2. So we have some proportions that we can look back and get from the chemical equation, okay? So let's start with 1,256.0 moles of FeS2. And we want to figure out first how many moles of oxygen are needed to completely react that, okay? So moles of FeS2 goes on the bottom because we want to get rid of those units, and we want to find out the moles of O2. That's what goes on the top. Okay, and now comes that proportion that we know from the balanced equation. So we have 4 moles of FeS2 are needed for every 11 moles of O2. Okay, and then we multiply 1,256 times 11 divided by 4, and our answer is going to come out to be, where's my answer? 3,454.0 moles of O2. And we circle it for our favorite teachers. Teachers like to see circled answers. They're much easier to find. So that's how many moles of oxygen would be needed. Now we were also asked to calculate how much iron oxide would be produced. We do it in the same way. We start with 1,256.0 moles of FeS2, multiply it with moles of FeS2 on the bottom, and our new units, what we're looking for on the top, which is moles of Fe2O3. And then we plug in the proportion. There were 4 moles of FeS2 for every 2 moles produced of Fe2O3. So we would put this in, multiply 1,256 times 2 divided by 4, and the answer would be 628.0020, so that we have the correct number of significant figures, moles of Fe2O3. So that's how we can, again, fully analyze chemical equations. If we know our starting amount of one reactant, we can figure out how much of another reactant we need to fully use this up, or we can figure out just how much product we're going to end up with. So that's on your own 6.2. Now we're going to do on your own 6.3.